Hello and welcome back to my channel Learn with Nikhil. So in our previous lecture we have seen how the robot moves in 3D space with respect to the rotation and the orientation. In this lecture we'll see the kinematics and dynamics of the robot using this DH parameters. So let's begin. So in our previous lecture we have studied that we have 6 degrees of freedom. So to reach at a particular point of a robot, we require 3 positions and 3 orientation, total 6 parameters. But Danawitt Hartenberg suggested that only 4 parameters are sufficient to make the robot work. So we'll see that. So to understand the DH parameters, first we will understand the concept of frame and line. So I have this frame, this is the 3D frame, and we have a line which is in 3D space. This whole thing is in 3D space. Now I have to travel from this frame to this line. So if I have to connect this frame to this line, the method is that first step we have to draw a line parallel through this Z axis. So we have drawn a line parallel from this Z axis. Then we have to draw a common normal attaching both these lines. So here you can see I have drawn a line which is called as common normal. And what is a common normal? It is the shortest distance between the Z axis and this line, this frame and the Z axis. And the thing with this common normal is that it is 90 degree to this line also and 90 degree to this line also. As this is in 3D space, here it's looking like an angle, but this in 3D space it is here a 90 degree and this is backward. So here also it is 90 degree. So common normal is nothing but a 90 degree line between both these lines. So here also it is 90 degree and here also it is 90 degree, which is perpendicular, and this line is called as common normal. Now the height at which this frame is transferring on this line, as you can see here. So if I have to reach at this particular point, from here the frame is here and we have to transfer it till this point. First we have to extend it at an height of B. So here in some of the books it is denoted as D, here I am considering B. So it is transfer at an height of B. So this transferring of at a height of B, it is written translate ZB till the intersection of Z axis and the common normal, and this is called as joint offset. So this B is nothing but called as joint offset. Next, if I have to again reach at this particular point, so now I have to rotate this frame onto this axis. So first I have transferred along the Z axis, so we have translated along Z axis, that is called as joint offset. Now we have rotated this frame. Now if I have to rotate this frame, I am rotating along Z axis. So Z axis remains on this line and the X and Y axis is rotated along this frame. So it is rotated at an angle, and as you can see the X axis now becomes parallel with this common normal. So we have to rotate in such a way that X axis comes in parallel and it gets aligned with this common normal. So we have rotated this frame along Z axis. So this angle is nothing but we have denoting it as theta, and this theta angle, it is called as joint angle. So we have rotated along Z. So when we have rotated along Z, we have written it as Z theta, so that X axis aligns with common normal. So first step we have raised this, transfer this at an height of B. So translated along at a height of B, that is called as joint offset. Next we have rotated this along Z axis. So Z axis remains common at an angle of theta, and that is called as joint angle. Now next we have to transfer this frame from this point to this point. As you can see, we have to transfer this frame from this point to this point. So we have transferred this frame, and this transformation of frame, we have the distance. So it has traveled this distance, the common normal distance. This common normal distance is denoted by symbol A, and it is known as link length. So as you know, this is one link and this is another link. So the distance is nothing but link length. So we have translated along x-axis. So as you know, we have translated along x-axis till the intersection of common normal and the link length, and common normal and the line, and that is called as link length. So this distance is called as link length. So this is the first parameter, that is B. This is the second parameter theta. This is the third parameter A. Now finally we have to align this with respect to this line. Now as you know, always the z axis should be aligned with the line. Here also at the start the z axis was aligned with this line, and now finally here also the z axis should be aligned with this line. Now to align the z axis onto this line, finally we have to rotate this frame again, so that the z axis will be aligned on this line. So here you can see we have rotated along x axis. So we have rotated this frame along x axis. We have rotated in such a way that the z axis gets aligned on this line. So we have rotated with an angle of alpha along x axis, and the z gets aligned on this line, and this rotation of an angle alpha is known as twist angle. So rotate x alpha so that the z axis aligns with the line is called as twist angle. So these are the four parameters. First is nothing but we have to transfer this frame onto here. So we have to transfer, this is one link, this is another link. So we have to transfer from one link to another link. As in a robot, we have to find the transformation from one link to another link, so that we can find the coordinates. So first step is we have to raise it at a height of d till it reaches the common normal point. So this is called as, this is B. Okay, so this height is denoted as B, or it can also be denoted as D. So this is joint offset. Second, we have to align x axis always onto the common normal line. So to align the x axis onto this line, we have to rotate along z axis. Now to rotate along z axis, we have to twist it along z axis, and we have to get this line onto x axis. So the common normal and the x axis comes in one line, and then we have to, so this rotation is nothing but theta, that is called as joint angle. Now we have to transfer this from here to this point, and the transformation from this to this point is nothing but A, that is called as link length. And finally we again have to align the z axis line onto this line, and for that we have to rotate it along x axis, that is the angle of alpha, and that is called as twist angle. Now I'll explain the DH parameters using different examples. So here we have a 3D plane, you have the x axis, y axis and the z axis, and here I am going to consider a robot which is moving in a 2D space. So this robot is moving in x and y plane only, so it is moving like this. Now if you analyze this robot, it has two joints, this is joint number 0, this is joint number 1. This is the end effector, or it is called as a gripper. Then you have two links, this is link 1, this is link 2. Now according to this, using the DH parameters, we will find the position of this end effector. Now for that, first we have to find the DH parameter. Now we'll build this robot. So this is the first link, this is the first joint, and this is the first link. The length of this link is denoted as L1. Now as you can see here, this link is moving in this XY plane and the Z axis is coming outward. So if I have to move this along XY plane, if I have to change the coordinates of the xy plane, we have to rotate it along z axis. So you have to rotate this frame, this link along this z axis. So this is the current x0, y0. So now we'll move this along z axis. So this will be new x0, y0, and the movement of this with an angle of theta 1. So we have rotated this link with an angle of theta 1 along z axis. So this is the first link, this is the first joint. So we have to find the DH parameters for this joint also, and also as there are two links, the next link, first this next link, this x1 is in parallel with x0, y1 is parallel with y0, and again the z axis is coming outward. So z axis are also parallel to each other at this particular point. Now next, this link is also twisted at an angle of theta 2. So it is again rotated at an angle of it is rotated about z axis, and here it is rotated at an angle of theta 2. So this is theta 1 and this is theta 2. The length of the link, this is L2, and this is new x1 and y1. So we have rotated this along z axis. Now you should keep in mind, so this z axis and this z axis is parallel to each other. So the joint offset is 0, as here also the joint offset is 0, here also the joint offset is 0. It is rotated along z axis, and this link length, the x should be in line with the link. So here also the x should be in line with the link, here also this x should be in line with the link. So now we have to find the DH parameters for this robot. So DH parameters are according to the links. So this is the final end effector. Here also we have plotted the coordinate, this is x2 and y2, and this is qx qy. So this is the coordinate qx qy which we have to reach. So we have to reach this point using the angles and the link length. So for this we have to find the DH parameters. So DH parameters are the 4 parameters which we had studied earlier. So we have to find the DH parameters for this particular robot. Now to find the DH parameters, you have to draw this table. This table, the DH parameters, I'll explain with the Robo Analyzer software also, which will be very helpful for you to understand in a much better way. So the 4 parameters are joint offset, which is denoted by B. In some books it can be denoted by D. Joint angle theta, link length is denoted by A, and twist angle is denoted by alpha. And this is the joint. So as we have two joints, this is the joint number 0, this is joint number 1. So this is joint number 0 and 1. So these are the two joints. So we have to find the DH parameters for these two joints only. So we have to find the DH parameters of joint this with respect to this, then we have to find the DH parameters of this with respect to this. So let's see how it goes. So for the link 1, so for this first link, the joint offset is 0, as I have told that it is not moving along the z axis, and this length it is not there. So this joint offset remains 0. Then the joint angle is theta 1. So this angle is theta 1. We have rotated along the z axis. So this is the joint angle which is denoted by theta 1. The length of the link is denoted by L1, and finally the twist angle is again 0. So there is no twist angle. So as this x0 is in line with the link, so there is no twist angle, so it is 0. Same thing, we have to find the 4 parameters for the link 2 also. So for this second link, again the joint offset is 0, as it is not moving the z direction, and this z is parallel with this z. So the joint offset is 0. Again the joint angle is theta 2, the link length is L2, and the twist angle again here is 0, as this x is in line with this x. So this twist angle is 0. So as you can see from this diagram, that the theta 1 and the theta 2, we can say this is theta 1 plus theta 2, the whole angle reaching this particular point can be theta 1 plus theta 2. So this is how we have to find the DH parameters of any given particular robot. I'll take more examples with the Robo Analyzer software also, which will make this thing crystal clear. I'll explain this using Robo Analyzer software also. So as you can see, this robot, it has 2 degrees of freedom, it has 2 links and 2 joints, and it has an end effector. So it has 2 degrees of freedom. So in Robo Analyzer software, this is the home page, and here you can see we have selected this. By default it is 2 degrees of freedom, and this is 2p, that is 2 prismatic, but we want 2r, that is 2 revolute, as these 2 joints are the rotation or the revolute joints. So z axis is coming outwards, and z axis, through z axis the rotation is happening. So here also this is the z axis, this is the z axis, and about z axis the rotation is happening. Now these 2 z axes are parallel to each other. If you can see the front view here, or you can see the top view, this is the top view of the robot, as this is also the top view of the robot. It is in 2-dimensional. We can arrange this as per required. If I make this 90, this is the initial position and this is the final position. Initial position for this is 0, final position is 90. So when I move this using the forward kinematics, this will move like this, 90 to 180, so 90 degree it has moved. So this is rotation from 0 to 90 degree, and this is also rotation from 0 to 90 degree. I'll reset this. So this is the initial value and the final value. So in rotary joint, as you know, the theta value is variable. Here also you can see first option is the joint offset link 1. This is the link 1. Joint offset is 0. Now what is joint offset? As we have discussed earlier, it is nothing but the distance of this joint. So if I increase this joint offset to 0.1, so this movement, this axis, now it is here. So first it will move upward. It will move in this direction across the axis at a height of 0.1. So if this is 0.2, this height will increase accordingly. But now the joint offset is 0. So the height is 0. Then the joint angle theta is theta 1 and theta 2, that is variable. So this is variable, so you have the initial value and the final value. So this is variable, you can change the initial values and the final values of the links. Now by default it is 0 to 180. So if this moves, if I get this into top view, so this link will move from 0 degree to 180 degree. So this link initial starting position, this is 0, so 180 degree, this will be 180 degree, and this is 0 to 90. So this is 0 to 90 means this will move from this angle to this angle. So you can just visualize it. This is moving 180 degree and this is just moving 90 degree. So this link has moved from this position to this position, and this link has moved from this position to this position. Okay. So next is the link length. Link length is nothing but this length, that is 0.2. It is 0.2, 0.2. You can change it accordingly you want. Make this 0.3. This will increase. And finally, these are the initial values and the final values. So you can see the movement also. I can see the movement from this. I can visualize the movement. So selection, this is joint 1. Joint offset is 0, so it is there itself. Then next I'll click on joint angle. So this is the joint angle. Joint angle is the variable angle. Always the z-axis gets aligned to this. If this z-axis is not aligned, then it will get aligned and there will be an angle. Then link length, it has moved 0.2 meters. Twist angle is again 0. As you know, this Z is parallel to this Z, so the twist angle always remains 0. Now for joint 2 also you can visualize, joint offset is 0, joint angle is variable, link length is 0.3 now, twist angle is 0, so there is no rotation. Now let's see if I change this, how it goes. I write here 0.1, this is the joint offset, then link length I'll make it 0.2 only, twist angle I'll give it as 90 degrees, and remaining part let's keep it same. Now joint 1, now here you can see the Z axis, this is the Z axis coming outward. Okay, so this is the Z axis coming outward, and Z axis coming out from this is like this. So first is joint offset. So joint offset is 0.1. So this is the initial coordinate. This is the Z axis. So first it moves from this point to this point. It is traveling a distance of 0.1. So this is the joint offset. It moves along Z axis. It always moves along Z axis. Then next is joint angle, that is variable. Now link length 0.2. So this is the x axis. Link always gets aligned to x axis and it gets travel like this. Now here the twist angle given is 90 degree. Now the thing is that always the Z axis should be aligned to the rotation. So this Z axis should be aligned to this rotation part. Now this is the initial stage of the Z axis. This is the stage we require. So to move this, we have to rotate this Z axis at an angle of 90 degree. So the Z axis is rotated, and this is the x axis. X axis is again in line with the link only. So the thing we want like that. So x axis should always be aligned to the link, and Z axis should be coming out of the joint, or in other words it should be the axis of rotation. And the joint 2 is same. I'll make few more changes. Let's change this twist angle to 45 degree. So now the Z axis is like this. Okay, so it always gets aligned like this only. So it changes as per. So this has been rotated to 45 degree. So this is the 4 parameters, that is the DH parameters. In next lecture, I will take few more examples on DH parameters which will make this clear. Thank you for watching. Do subscribe to my channel. If you have any doubts, let me know in the comment section.